Hello everybody, in this lecture we're going to discuss a numerical example of the backpropagation algorithm. So in this network, as you see, we have a 2 by 2 by 2. We have two inputs. So these are the inputs, two inputs. We have the first layer, which is this one. This is the first layer. So we have here also two neurons for hidden layer, and we have here the output, which also constitutes of two neurons for output. So the input layer has a superscript of 0, as you notice here. This is the bias, and we have x1, x2 is the input, which we're gonna conveniently call it y1 of 0. So this, when we say y1 of 0, we mean this is layer 0. Layer 0 is the input, okay, and y1 is the first input, y2 will be the second input. In this case, we have y1 of 1. This means this is the hidden layer, first input, and the last layer, which is layer 2. Instead of having y will be y2. y1 of 2 will be equal to output 1. Okay, so this is the output layer. For each of the layers, we have weights, w1, 0. We always take the first subscript as the connecting neuron, and 0 will be the input neuron. So we have w of 1, 0, w of 2, 0. And of course, the superscript 1, which indicates that it's going to the hidden layer. If we look at the next layer, the output layer, we see that the input here is y0, which is the first one, of 1. So this is the hidden layer. And w1 of 0, so w1, 0 of 2, which is the second layer. Of course, this is the bias. The bias is w1, 0. So we have y1 of 0 input, y1 of 1 hidden, and y1 of 2, which will be the output layer. Now, if we consider this network and we want to compute the forward path, so first let's check out the inputs. So with the inputs, we have x1, x2 equals 0.05 and 0.1. We have d1 equals 0.01, d2 equals 0.99, and we have these small values for w1 for these are for the hidden layer, and this is for the output layer. We have learning rate of 0.5. We're not going to use any momentum, and the logistic function is being used for activation function. So let's start with the forward path. So we're going to start with epoch 0, and this we're going to do the forward path, which is going to be calculating the forward path from the input to the output. So with the forward path, we're going to write the formula, which is Vj of 0 in layer L will be equal to summation for all input neurons Wji of, this is epoch 0 of L, times Wi of 0 for the previous layer. Okay. So in this case, this is neuron J, okay, in layer L, and this is the weights, of course layer L as well, and these are the inputs from previous layer. So for the case of V1 of 1, so we have neuron J is equal to 1 and L is equal to 1. So let's start the first case by saying case of hidden neuron J equal 1 and L is equal 1. So now if you want to place the formula, we have V1 of 1 is equal summation I equals 0 to 2, since we have 2 neurons, and we have W, so in this case J is 1, so W1 I of 1 times Yi of 0 is the input. So in this case we expand, we start with I equals 0, Yi 0 of 1 for epoch 0, of course this is for epoch 0, times Y 0 of 0 plus W 1 of 1, this is for I equal 1, times Y1 of 0 plus W 1 2 of 1 times Y2 of 0. So this is I going from 0, 1 and 2. So now we need to compute those three values. So we know from the given that we have W1 of 0 of 1 is 0.35. So this is 0.35 times W0 of 0 is 1. This is the bias. We cannot find it in the input because this is the bias. We have it here plus 1. So now times 1 plus W11 of 1 is equal 0.15 times the first input is 0.05 plus W12 is equal 0.2 times W2 of 0 is 0.1 in this case, and if we compute this it will be equal to 0.3775. So this is V1 of 1. So now we got the first, this value. Now we need to get V2 of 1 also. But before, let's continue and find what's the activation of this value. So we know that Y1 of 1 of 0, of course this is all for iteration 0, is equal to the activation function of V1 of 1 of iteration 0, and this will be equal, based on the formula, 1 over 1 plus e to the power minus 0.3775, which will be equal to 0.5933. So this is equal Y1 of 0. Okay. Now let's do it for the second iteration where we have V2 of 1. So now to do the second iteration, so now we need to compute V2 of 1, which is going to be equal summation, this is of course of iteration 0, summation I equal 0 to 2 for W to I of 1 in this case times Wi of 0, and we're gonna place this is W2 of 0 of 1, of course of epoch 0, times Y, this is 0 of 0 plus w, of course, of iteration 0, w21 of 1 times w1 of 1 of iteration 0 plus w22 of 1 times y1 of 2 of epoch 0. In this case, this will be equal to 0.35 times 1. This is the bias, plus we have 0.25 okay, times 0.05 plus 0.3 times 0.1. This will be equal to 0.3925. So this is V2 of 0 of 1. So we found the second induced field. Now we want to find Y2 of 1. So of course Y2 of 1, Y2 of 1 of iteration 0 is equal 1 over 1, since we're using the logistic function, which is going to be equal to 0.5969. This is equal y2 of 0, 1. Okay. Now, so we got the inputs for this layer. We have, this is 1. This is y1 of 1. We already got it. y2 of 1. We already calculated it. Now we're gonna find the next v2 of 2 and v1 of 2 and v2 of 2. So for the output layer, we're gonna use a different. For the output layer, we have j equal 1 and L is equal 2 in this case, indicating that it is an input layer. Okay. So for this case, we have V1 of layer 2 is equal to the summation of I, of course, going from 0 to 2. For, in this case, we have W1I of 2 times yi of 1. Of course, this is for iteration 0 or epoch 0. So in this case, we have w11 of 2, 10 of 2 of 0 times y w1 1 of 0. So what we're trying to do here, if we look at the figure, we have this and we're trying to calculate this. So we multiply this weight by 1 and this weight also will be multiplied by 1, and then we multiply this weight by y1 of 1, which we computed, and this weight by y2 of 1, which we also computed. So this will be as follows. So now we have, well, this is j equal 1 and L equal 2. So we go ahead and start plus w11 of 2 times y1. This case, this is, it should be 0. This is y1 of 1 of 0 plus w12 of 2 times y2 of 1 of 0. So this will be equal to 0.60. If you look at the inputs, these are the weights for the output layer. 0.60 times this is 1, the bias, plus 0.5 times the first one that we computed, which is 0.5933, plus 0.55 times 0.5969. These are 1 of 1, and this is y2 of 1, okay, which will be equal to 1.1059. This is will be v1 of 2, the second induced field of the output layer. Now, of course, to calculate the output, since we are at the output layer, as you can see here, we apply the activation function to 1.1059, which will be equal to 1 over 1 plus e to the minus 1.1059, which will be equal to 0.7514. So this is the first output. Now if I want to calculate the second output, this means we're still at the case of the output layer. We have j equal to, and L of course is equal to output layer, and we have now the second induced field of the first epoch is equal to summation for I equals 0 to 2 for W2I of, in this case, 2 times epoch 0 times yi of 1, the layer just before it, of epoch 0. This will be equal to W2 0 of 2 times W, in this case I is equal 0 of 1 of 0 plus W2 1 of 2 times y1 of, or this is the first one, this is 1 for clarity, and plus W2 2 of 2 times y2 of 1 fourth of epoch 0. This will be equal to 0.6 times 1 based on the input. This is given. All of these are given for the first epoch. And then we have W21, which will be 0.5 times 0.5933 plus 0.55 times 0.5969. These are computed from the previous iteration, and we have 1.2249. Of course, now to calculate the output, which is y2 of 2 of 0, which is equal to output 2, is going to have the activation function of 1.2249, which is equal to 1 over 1 plus e to the minus 1.2249, which will be equal to 0.7729. So this is the second output. Now to calculate the error, we need to differentiate, to subtract between the calculated y and the desired output. So if we check at the error, we have ej of 0 is equal dj of 0 minus oj of 0. In this case, and also we have the instantaneous error is equal half ej of 0 squared. Now, for the output layer, this is of course for output layer. Now, if we check the output layer, we have E1 of 2 of 0 is equal to D1 of 0 minus O1 of 0 is equal to 0.01 minus 0.7514. This is given, this is calculated. So we have 0 minus 0.7414, and E1 of 0 is equal half minus 0.7414 squared, which is equal to 0.2748. Now for the case of E2 of 2, it's equal to D2 of 0 minus O2 of 0, which is equal to 0.99 minus 0.7 0.729. This will be equal to 0.2171, and E2 of 0 will be equal to half of this value, 0.2171 squared, which will be equal to 0.02356. Okay, the total error is equal summation for j belonging to C for ej of 0, and in this case it will be 0.2748 plus 0.02356, and we have the average, the total error of 0.2989. So now we calculated the error, we calculated the forward pass. So what about the backward pass? So for the backward path, we need to update the weights. So the most important part of the backpropagation algorithm is weight update. So backward pass. So here we're trying to update the weights. So now the weight update equation starts like this. The weight wji of L of 1, this is next epoch, is equal wji of L of 0 plus learning rate times the local gradient at L times ya L minus 1 for 0, where alpha is equal to 0. Now, so we start from the output layer in this case. So now what we're trying to do is we calculated V1, V2, and Y1 of 1 and Y2 of 1. And now we calculated O1 and O2, and we calculated the error. Now it's time to go with the backward path. So we start here and then we propagate inside. So with the output layer, the case for L equal 2, start of course as always J equal 1, you're in J. So W11 of 2 is equal, of course this is of iteration 1, is equal to W11 of 2 of iteration 0 plus the learning rate times the local gradient at the output times y1 of 1 of 0. So let's see what we have. This is the previous weight. This is equal 0.4. This is the learning rate equal 0.5, and this value is 0.5932. We already computed this value. So the only unknown in this equation is the gradient, the local gradient. So what is the formula for the local gradient? It's equal E1 at 2 times phi activation function, the derivative of the activation function of the induced field at this point. So if we take the logistic function, the derivative is, if we take the value, so phi 1 of v2 of 0, v1 of, and this will be equal to O1 of 0 times 1 minus O1 of 0. And in this case, for the case of A equal 1 as in the given, so we will have 0.7514 times 1 minus 0.7514, and this will be 0.1868. Now we plug this value here and we'll get WY11 of 1, this is the next weight, is equal 0.4 plus 0.5 times 0.1868 times 0.5932, which will be equal to 0.35891. In a similar manner, we need to calculate the weight update for W12 of 2, W21 of 2 of 1, and W22 of 2 of 1. And for these, the values, you can work them yourself. This is equal to 0.40867, and this is 0.51130, and this is 0.5613. And of course, for these two, we have the second graded local gradient is equal to 0.038107. Okay, now this is for the case of the output neuron. What about the case of the hidden neuron? Case hidden neuron, J equal 1. So we updated these weights. Okay, these are all the updates for these weights. Now we need to update the weights of W10 of 1 and the rest. So for this case, each weight will be done separately. So W11 of 1, this time of the first layer, is equal to W11 of 1, the old one, plus the learning rate times, in this case, the local gradient at this level, y1 of 0. This is the input. Now for the local gradient, it's equal to phi 1 prime of v1 of 1 of iteration 0 times summation k equal 1 la 2 for the local gradient at the output times wk1 of 2 of 0. So this is the formula. Remember, these are from output layer, or the layer. If we have two hidden layers, this will be for the second hidden layer. So now we have, so let's find each parameter by itself. So phi 1 prime of v1 of 1 of 0 is going to be equal to y1 of 1 to 1, since previously we used the output, since y1 of 2 was actually the output. Since now the output is for the hidden layer is y1 of 1, we use y1 of 1 minus y1 of 1 of 0. So what I mean by this is that here I could have used y1 of 2, for example. Okay, and here I can use y1 of 2 instead of output. They are the same. So this is the output layer, and this is the hidden layer. So this will be equal to 0.5933 times 1 minus 0.5933. This is equal to 0.2413. Now we need to, so we calculated the activation function, the derivative of the activation function at the first hidden neuron. Now I need to calculate the summation. So the summation, so what do we mean by summation? It's going to be equal summation k equal 1 to 2, which is the number of outputs, the local gradient times wk1 of 2 of 0. So this will be equal to the first local gradient for k equal 1. Remember, k starts from 1, not from 0. Of 0 times w11 of 2 plus, this is the second one, times w21 of 2 of 0. This will be equal to minus 0.1385 times 0.4 plus 0.038107 times 0.5, and in this case we will have minus 0.03635, and in this case gamma 1 of 0 is equal to 0.2413 times minus 0.03635 to minus 0.00877, and in this case we can go ahead and say w11 of 1 of the next iteration is equal to w11 of 1 of the previous iteration plus 0.5 times minus 0.00877 0.05, and this will be equal to 0.15 minus 0.00219, which equals to 0.14978. And similarly we can work our way with w12, w21 and w22, and this finalizes the example.